Okay, here we are with 8.1, estimating mu when the standard deviation is known. Some assumptions on the random variable x. We have to assume that it's a simple random sample of size n that comes from that population. So I'm grabbing the same sample size each time, and it comes from that same population. The value of the population standard deviation of that population is known. X is normal. And if we don't know that the distribution is normal, then my sample size has to be bigger than 30. Okay. And it's definitely going to be some sort of mound shape. Usually, the bigger that n is, the more chances it's going to be 30 or closer to 30. Well, we really don't know what mu is. Mu is a parameter. We have an estimate that's a lot easier to get, and that sample statistic or point estimation for mu is x bar. So x bar is an exact number that I know the value of that I can kind of use to make an assumption based on mu. Now, before we might assume that x bar and mu are the exact same. Now we're going to come up with an interval that mu is going to be between. So margin of error, even though it takes very large sample size to be different from mu, the margin of error is just basically whatever your score is that you've got, take away that mu and take the absolute value. Margin of error is a positive number that we're okay with being away from. Now, the level of confidence, or the confidence level C, is any value between 0 and 1. Usually as a percentage is what they're listed as, so between 0% and 1%. That corresponds to the area underneath the curve on the standard normal curve between negative z with a little c and positive z, a little c. So essentially, if I want to be 95% confident, I have to have 0.95% of the area between the curve so that it's symmetrical at a negative z-score and a positive z-score. Okay, and what we're actually finding with these critical values or this confidence level for C is we're finding the probability that it lies between those two z-scores. Okay. Kind of theoretical, but we'll talk it through a little bit here. So the example I guess they are going with is the 99% confidence interval and how to find the z-score for that. You can use the table. So when you see the z-score, you'll see a 0.99 below that. That means that we're talking about 99% of the data between that positive z-score and that negative z-score. Right? Well, to use the table, we would not look at 0.99, but rather look at 0.005. And here's how we came up with that. You're going to take 1 minus 0.99, and that's left with 0.01. But that needs to be split amongst both the lower tail and the upper tail. So divide that out and you get 0.005. Look up that 0.005 in the table for the area underneath the curve, and it lands between 0.0051, 0.0049. So that means that our z-score is going to be between 0.07 and 0.08, or negative 0.507 and negative 5.8. So I believe the one we go with for that is this 2.58. That means that the lower negative 2.58 and positive 2.58 should get you an area underneath the curve of 0.99. Right. Now that I've gone over all that, if you look on page 408 or even in the back of the book under the z-table, there's this little table that gives you all the z-scores anyways. So you don't have to keep on looking up the areas over and over. If you want to be 99% confident, there's the z-score you're going to use. If you want to be 95% confident, there's the z-score you're going to use. Okay, all those z-scores are there. You don't have to worry about calculating them. So a little bit more of a development here. Remember from the sampling distributions for X bar, when we're doing the central limit theorem, or again, just we know the population is normal, the mean we're going to use is going to basically be the population mean. Okay. In a way, we're actually not going to use this at all. It's this number is the one we're working with. But our standard deviation does have to get adjusted, so you'll take that population standard deviation and you'll divide by the square root of n. Kind of coming back to that whole z-score thing, you're coming up with an interval, a confidence interval, where you're going to take this standard deviation and you're going to find how many standard deviations away you are below the mean and how many standard deviations away you are above the mean. Your confidence level is going to dictate the z-score. You're going to add and subtract your average. But the problem is we don't know the actual average. So we'll take the mean or the sample mean that we got from our sample of 30 pieces of data or maybe 5 pieces of data, whatever sample size it was, and we're going to come up with this confidence interval. Yeah, I'm going to kind of skip ahead of this one to get to it a little bit more. But it's basically coming down to we need to know the population, or so since the population mean is unknown, but we need to know the population standard deviation, we can come up with this error by taking whatever z-score you've got and multiplying it by the standard deviation divided by the square root of n. Okay. And to get your confidence interval, you're taking the sample mean and you're subtracting your error, and you're taking your sample mean and you're adding error, and you're going to be some level of confidence that this population mean that is unknown falls between these two numbers. Okay, pretty theoretical. Hopefully we can kind of get to a little bit more of a concrete example, and that might help out. The salaries of a community college math instructors is historically known to be normally distributed. That's good. That helps us with the fact that we don't need a sample size that's bigger than 30. With the standard deviation of 3,500. Okay, using a telephone, they randomly asked 33 instructors and calculated the mean average to be 53,128. Okay, it's also bigger than 30, so we can go ahead with the normal curve anyways, but because we knew it was normally before, we don't necessarily need to have it be 33. We don't know the population mean, and we're going to construct what's a 95% confidence interval for the population average. Yeah, I'm just going to double check real quick. There it is. N is equal to 33. So those are the 33 instructors that they interviewed. Your sample from those 33 was $53,128. The population standard deviation was $3,500. We wanted to be 95% confident, so we looked up that z of 0.95 to be 1.6. So to find the error is 1.96, the z-score that we looked up in that back little table, the population standard deviation, and divide by the square root of 30. And the error works out to be $1,194.17. So to get my confidence interval, remember an interval is a lower number and a higher number. We're going to take the x bar, the average that we got from those 33, subtract the error, take the average, sample average, and add the error to get a lower and upper number. So we can say that we conclude that within a 95% confidence or 95% confidence interval, that the interval from $51,933.83 to $54,322.17 contains the mean salary of all community college math instructors. In other words, we don't know what all of them make, but we're 95% sure that it's between those two numbers. Which is really helpful because it's a lot easier to get a sample mean than it is to get a population mean. Okay. The thing with confidence intervals is if we could repeat this confidence interval process multiple times with random samples of equal size, some intervals would capture mu and some would not. So in other words, just because we're 95% confident doesn't mean that we actually got the actual population in there. Also, we could run this through again, get a different average, and come up with totally different results. Okay, so it's kind of dependent on the sample mean that you got. Confidence level is an approximate proportion of intervals that will capture the population parameter. Okay, so our shot is to get 10 timer. Okay, multiple confidence intervals. So here's a 0.5 or 0.9 confidence intervals for the sample size. It's the same size. So basically, if they did this once, twice, 13, 14, 15, 16, I'm sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times, all these intervals are these 10 possible confidence intervals. You notice how one of them doesn't even hit the actual population. Okay, so you do run the risk that you don't have your mean in there. Okay, on page 408, problems number 1 through 9, give those a shot or give a couple of shots till you get the hang of it, and we'll talk about it more in class.